As we move in forecasting to learning how to use data, it's worth considering again the difference between the sample and the population. We are taking information from a sample to learn about a population. So thinking about the types of pieces of information that we're learning from the sample, we are learning different outcomes associated with random variables. And we may be weighing those outcomes according to the number of times that we see those particular outcomes in our data set. So as we think of probability distributions associated with random variables, it's worth considering that when we have a sample of data, we are essentially attempting to construct a proxy for this probability distribution based on the information that we have on hand. And we do that for all the data that we collect. And so as we think of trying to relate data to each other, when we have two random variables from a population, they can be related to each other via methods like covariance. And if we know the probabilities and the outcomes, then we can construct the covariance from the joint probability distribution. And if we don't, we can still estimate a covariance. We can estimate a relationship between those two variables, but it will be predicated on it being a sample rather than the population. And so as we work toward analyzing samples, this lecture is going to dive a little bit deeper into how those population relationships behave, because what we're trying to do with the sample is provide the best representation of that population relationship that is available to us based on the data that we have on hand. So understanding how the population behaves is important because we're actually trying to replicate that insight via data analysis. Okay, so a couple recaps from previous lectures. Let's have a look at these data right here. These are wage earnings in the United States. And this is from the book that I'm having you read for econometrics, the lecture notes from Bruce Hansen. This is on page 10. Take a look at these data. The data are from the 2009 Current Population Survey. This is a cross-section of about 50,000 respondents. And they describe different features associated with their lives, and one of those features is their hourly wage. And so this is a sample from a population. Now let's take a look at the graph on the left. The graph on the left estimates what we described previously as a cumulative distribution function. So it is tracing out a smooth function right here, based on the respondents from the Current Population Survey. And as we look at the bottom left, you see that there is zero probability associated with people earning or reporting an hourly wage of zero here. But as we start to go up in dollars per hour, you can see that roughly 15% of the sample earns $10 an hour or less, but then the median is just beneath $20 an hour. And if you look at $40 an hour, 90% of the sample earns $40 an hour or less. So if you think of the median $20 an hour, that would be roughly equivalent to a job between, say, $35,000 and $38,000 a year. Which is kind of consistent with what your expectations might be starting out in a new profession as a college graduate. We're hoping for more, but that's the median that's in this data set. So this is a representation of the cumulative distribution function, and it is an estimated cumulative distribution. So this is not the true cumulative distribution function for the United States working population, but it is our estimate of this relationship based on responses in the current population survey. And you can see here that the right graph shows you a probability density function. So a bulk of the observations, as you can see, are between $10 and $40 an hour. So if you look here, about 80% of the data is within $10 and $40 an hour, going from 0.1 to 0.9. And if you look underneath this graph, about 80% of the area is between $10 an hour and $40 an hour. So on the graph on the left, probability is directly assessed on the y-axis going from 0 to 1, but in the graph on the right, the area is a description of the probability. So let's go back to the idea of knowing information about two variables. And let's go back to the example that we had in class in the previous videos, where x takes the value of 3 or 4 with equal probability, and y takes the value of 1 with probability 0.75 and 2 with probability 0.25. So x, you have a 50-50 chance of 3 or 4, but y, it's more likely to get an outcome small y of 1 rather than an outcome of 2. Okay, so now suppose you only observe y equal 2 when x is equal to 4. So the probability of y equal 2, x equal 4 is 25%, because every single time that y is 2, we know what the value of x is. The value of x is 4. Well, based on that, we actually have enough information to identify the remaining probabilities. So when y is equal to 2 and x is equal to 3, that is actually something that does not happen. So we never observe y equal 2 and x equal 3, because every time that y is equal to 2, x is equal to 4. So if we look at the probability associated with x equal 4, well, that is a 50% occurrence, but 25 of that 50%, 25 basis points of those 50 basis points are associated with y equal 2, which means the remaining 25 basis points are associated with y equal 1. So when x is equal to 4, you have a 50-50 shot of seeing 1 or 2 for y, but when x is equal to 3, you have entire chance of just seeing y equal to 1. So the probability that x is equal to 3, y is equal to 1 is 50%. Every time that x is equal to 3, y is equal to 1. Every time when y is equal to 2, x is equal to 4. And there's just some remaining probability of x is being equal to 4, but y is being equal to 1. We call this set of 4 probabilities here, 0.5, 0.25, 0.25, and 0, as the joint probability distribution of x and y. So that's f of x comma y. It's a joint probability distribution. It describes the behavior of x and y together. So it provides insight as to where we might see particular dots in a Cartesian plane, for example. It also provides us additional information with which we can calculate the expected value, and that is a highlight of today's lecture. So think about it. Are the expected values of y and the expected value of y, given that x is equal to 3, the same? And the conditional, this is called a conditional mean. The expected value of y when x is equal to 3 is a condition that we're putting on the mean. So I'm announcing, hey, I know that x is equal to 3. Well, what do you believe y is? Well, we know there are only 2 values for y, 1 and 2. But every time that x is equal to 3, y is equal to 1. That is different from the expected value of y. So the expected value of y is 0.75 times 1 plus 0.25 times 2. That's 1.25. But the expected value of y, given that we know x is equal to 3, is 1. Knowing that x is equal to 3 allows us to uncover a more precise expectation for the mean value of y. Knowing a realization of x in general provides a more consistent expectation for the random variable y. Well, what if x is equal to 4? You announce that x is equal to 4, then half of the time y is still equal to 1, but half the time y is equal to 2, and so the expectation changes to 1.5. So the expected value of y when x is equal to 4 is different from the unconditional expectation of y, which is that it is equal to 1.25. This is a big deal. So conditional expectations provide us with an update about the likelihood of a particular random variable. And conditional expectations are a key component of statistics. So this is how x and y behave. It is for certain. It is a description of a population random variable. The probabilities and the outcomes are known. When x is equal to 3, we know that y is equal to 1. When x is equal to 4, we know that the expected value of y changes from 1.25 to 1.5. This is a known behavior, and what I want to get across in this lecture is that oftentimes we actually do not know exactly how y will behave for a given realization of x, but we are still trying to provide our best estimate for it. Okay, so in the previous example, knowing the value of x updated our expectation of the value of y. The interpretation is very important. So if I think about the outcomes as residing in a sample space, then I am reducing the size of the sample space for which I look for these different outcomes of y. So I'm looking in a smaller set than I was previously. And the conditional mean reflects this. Let me just change the conditional mean here. I believe I need to change it to 3/2. I thought I had typeset it. Let me just update that here, and then I'll reopen the file. This should be 3/2 here. Okay. The conditional, what I just want to get across is that the conditional mean changed from 1.25 to 1.5. That is a better estimate for the expected value of y. Note that 3/2 is not a possible outcome for y. So you cannot get 3/2 as a possible outcome, but it is our best estimate for the conditional mean. Okay, so this leads us to a new definition. This is called the law of iterated expectations. And what the law of iterated expectations says is that I can estimate the unconditional mean of x based on conditional means of x given y. So I can find the expected values of x based on how y and x are related. Okay, so let's go back to the previous example. The expected value of x is 0.5 times 3 plus 0.5 times 4, which is 3.5. So that is the expected value of x, 3.5. What is it if I account for how y impacts x? So the expected value of x given that y is equal to 1 is different from the expected value of x. If I know that y is equal to 1, if we go back to this joint probability distribution, then it's more likely that x is equal to 3 than it is that x is equal to 4. So 0.5 is the probability that x is equal to 3 when y is equal to 1. 0.25 is the probability that x is equal to 4 when y is equal to 1. So that ratio is 2 to 3. There's a 2/3 chance of seeing x equal 3 when y is equal to 1. There's a 1/3 chance of seeing x equal 4 when y is equal to 1. So the expectation of x, given that y is equal to 1, is 2/3 times 3, which is 2, plus 1/3 times 4, which is 4/3, for a total of 10/3. That is the expected value of x given that y is equal to 1. Now, when y is equal to 2, there's a 50-50 chance that there is no 50-50 chance. Every time that y is equal to 2, x is equal to 4. So when y is equal to 2, we know that x is equal to 4, and the expected value of x when y is equal to 2 is 4. There's a 100% chance. So the inner expectation of this parentheses is computed from taking a look at each possible outcome of y and examining its impact on the conditional mean x. So we looked at y equal 1, and we calculated the expected value of x as being 2/3 times 3 plus 1/3 times 4 for 10/3. Then we looked at the only other outcome for y equal 2, and we said that the expected value of x was 4. There's a 75% chance of being in the first category. There's a 25% chance of being in the second category. So we have 0.75 times 10/3, which is 3/4, times 10/3, which is 10/4. Then we have 0.25 times 4, which is 1. And we have 2.5 plus 1, that's 3.5. Note that this is the same as if we were just to multiply the different probabilities for x, 0.5 times 3 plus 0.5 times 4. Now you may be wondering, well, why bother with the law of iterated expectations, but take a close look at our expected value formula. It involves the probability of y equal 1 and y equal 2, but it does not require us to know the probability distribution of x. So if we know the joint probability distribution, we can calculate the expected value of x directly without knowing x's distribution. That's pretty useful. So I can evaluate the expected value of x without the probability density function for x. And practically speaking, this is what we're going to do with data. We are going to make a computation for an outcome variable of interest based on estimating a conditional mean for that outcome variable based on observed values of x and how often those values appear in our sample. Okay, so we defined small f of x as being the probability density function for x, and you can see that it is this graph right here. So if we look at a bell curve, that's small f of x. F of xy is the joint probability density function of xy pairs. So if you're thinking about what this would look like, you'd graph it in 2D space, and it would look a lot like a contour map, like a topographical contour map. So the different circles are the heights associated with the probabilities, and x and y take their own values in the top, in all quadrants of x and y space, I guess is a good way of putting it. But you'll measure the intensity of those values with a contour map. The marginal distribution, This is the distribution. This is a new definition. This is the distribution of x when y values are not taken into account. So I know the values of y here, okay? I know the joint probability distribution, so I could interpret this first sentence of 0.5 times 3 plus 0.5 times 4, that expected value, those 0.5s, I could have interpreted that as a marginal distribution where I didn't take into account the values of y at all. So if I know the values of y but don't take them into account, I could think of that distribution as being a marginal distribution. And if we look at the marginal distribution, it looks a lot like what we had before. We interpreted the previous distribution as a probability density function, that this is small f of x, but it is probably more reasonable to interpret it as a marginal distribution. Okay, so I want to introduce one more new term, and this is called a conditional distribution. This is the distribution of y for given realizations of x. So note that I put it in terms of small x. So you have one particular realization of the random variable x. It's been realized. What are the distributions of y? What does that look like? And it's so I take a value out of the possible values for x, and I look at that distribution for y. This right here, this 2/3, 1/3, is a marginal distribution. Is a conditional distribution for x given that y is equal to 1. So when these probabilities change based on a value of y, we call that a conditional distribution. Those probabilities changing are important. So we're often interested in estimating how, when we have some policy, how do the outcomes change based on doing something specific as part of this policy? And the conditional distribution will give us information associated with that. So think of it as a slice of the joint density function, but we just keep the value of x fixed. I fixed y here, and I'm just extracting part of the joint density. Okay, so I extract the values of x associated with y equal 1 and compute their likelihoods. Okay, so let's have a look at what a conditional distribution looks like in practice. Take a look at this graph. This is log wage density for females and males in the current population survey. Now, we use log wage rather than real wages, and the reason why is to make this graph look a little bit more like the normal distribution rather than this skew right graph that you see on this slide here. Take a look at this graph. The dashed line represents wage distributions for females. The solid line is for males. Note that the center of the distribution, you have a dashed line for the female and a solid line for the male, and you see there's a gap between the two genders. And this is done in 2009. We don't have the best representation of gender here. We're just kind of looking at a binary classification for gender, understanding that if we were to expand our definition for gender, we would have additional conditional distributions. Long story short, there's the gender wage gap right here. So there is a distribution of female earnings, and you can see that they're more tightly clustered around the dashed line. The probability is higher. And the male earnings, the mean is higher, and there's a lot more in the right tail. So there are many, many, many more high male wage earners than there are high female wage earners. And that can actually be seen in this graph. take a look at another distribution. This is also from the Hansen econometrics text. Here we have a line that takes into account two different X variables, gender and race. And again, with race, we just look at white and black, but obviously there are many other potential outcomes for the race variable as there are for the gender variable. Those are not accounted for here. What I do want to point out with this graph is that if you take a look at the dashed line for white males, has a mean here, highest mean, far and away the largest right tail. And then if you look at the solid line, that's white women, they're very comparable to black men, with black women trailing behind in this graph. So you can look at three separate means all trailing white males here in this graph. This is important information to know. So to the extent that you're concerned about these different gaps, an important question to ask is, what is the size of the gap and what is the spread of the gap? You learn that from the conditional distribution in the data. So this is an estimate of what the dispersion of wages looks like based on gender and race. So based on the information that they had on these X variables here, we are tracing out a conditional distribution. Okay, we are trying to estimate a smooth function that captures the probability of particular ranges of outcomes given these characteristics, and you're going to have a different smooth function for each of these realizations of X. Okay, and this is the link that we use to consider regression analysis. So now let's move away from this discussion of how the population behaves, knowing that we have just scratched the surface of it. We haven't talked about really continuous variables or manipulated them at all. We're going to move directly to the sample. And in particular, let's just pretend there are n different variables in the data set that could explain y, x1 through xn. And I want to combine these into a vector of variables. So think of a bunch of different columns in an Excel spreadsheet, and what I want to do is just slice it with a row and look at all the values in that particular row for those variables as being a vector of x. The expectation of the y based on these variables is what's called a conditional expectation function. Okay, so if I have a bunch of different realizations of different x variables in my data set, I use those realizations to provide an expected value for y. That's called a conditional expectation function. And we could rewrite it as the expectation of y given vector of x is equal to m of x. It provides an expected outcome of y for realizations of x. So it produces a number based on realizations of x, which are random. So the CEF m of x itself is also a random variable, because you're going to plug values of x in there and you're going to generate an expected value for y, and that's a random variable. Linear regression is a special case of a conditional expectation function. So when you fit a line through some data, you are estimating a very specific type of conditional expectation function. And that's the function that we're going to focus on in this class, so we're not going to do other types of modeling choices for the conditional expectation function outside of linear regression, but we are going to expand our analysis of this well-used typical measure of conditional expectations. So regression is our attempt to estimate the best CEF imaginable. Data are observational. As discussed in the Hansen text, it's going to be difficult to uncover causality in this type of data set. but they are representative of the population. So for every x variable in the vector of x, the data that we obtain are the only outcomes that we observe. So all we know about the variables in the current population survey are what those 50,000 respondents told us. We don't know of other relationships outside that. So I have an incomplete set of outcomes for x. I have an incomplete set of outcomes for y. I don't observe all the x that are possible. That is a sharp contrast to here where I observe 3 and 4 and that's it. Or where I observe 1 and 2 and that's it. Sharp contrast here. So I don't observe all the possible outcomes, and as an obvious point to this, I don't know the probability distribution of the random variable because I don't even know all the outcomes of the random variable, nor do I know the distributions for any of the x variables. So I'll estimate those probabilities based on the outcomes that I observed and the frequencies with which I observe them, but I don't actually know what they are. The data are representative of these random variables, but they themselves are not the population random variables. They're samples of it. So we're going to estimate the best m of x possible given what we have. Okay, so let's describe a new term called error. CEF error. So a definition, let's let E is called the error. It's the difference between the outcome y and our conditional expectation function m of x. So we plug in a bunch of values for these different xi, and it's going to produce an expected value of y given x. Expected value of y. So I think of this as being y minus the expected value of y given x. So it's the distance between those, the known realization of y and what we estimated that realization to be based on what we observed from x. And so because of this, the implication is that our data y is represented with our conditional expectation function m of x and e, which is the error term. So the expected value of the error is 0. E is what is unexplained. So I do not know why I got a particular error. So I did not explain that portion of y. M of x is the explanation we have for y. So here is the variation in y that I can explain based on what I observed, but there's some left over that's unexplained by the variables that are in my data set. Now, if I add in more variables, it should help reduce the amount of error in that I have more of an explanation. The expected value of the error given the observables is the difference between the data and the conditional expectation function in expectation. So it is 0. The expected value of the error squared is sigma squared. That is the regression variance. That is going to give us a description of the spread of outcomes of y. So conditional variance, the expectation of the error squared, is the variance of y given x. And it tells us how y might vary based on values of x. It's error squared because the expectation of the error is 0. So squared allows us to trace out some of that dispersion in the same way that a typical standard deviation or variance would work. We'll get back to these concepts of homoscedasticity and heteroscedasticity later, but the variance may be related to the x variables, and we have to think a little bit differently about it when it is. Let's look at the most common conditional expectation function. This is the linear conditional expectation function. So y is equal to mx plus e. Mx, I have a slope times x variable 1 plus slope times x variable 2 plus slope times x variable n. I could have n variables, so put some dots in there. This is the most typical type of conditional expectation function, and it is the one we're going to focus on estimating for cross-sectional data in this class. So we're not going to estimate too many other types of models. We're really going to focus on this linear conditional expectation function as a method for taking our data on x and producing an expected value of y. So it's called linear because these parameters are not squared. They are just straight line relationships individualized to particular variables. This is what Excel produces. So when you estimate a regression in Excel, you're estimating a linear conditional expectation function. Now, here are some conditional expectation functions in the CPS. Here is the relationship between years of education X and dollars per hour Y. Note that we've also included a race variable, white. The circles are for men, the triangles are for women, and we have the gender wage gap can be seen everywhere in this data. It's a function in that as I change values of education X, I trace out a new value of dollars per hour Y. You can see that it's flat, and there's a jump for high school, and then there's even more as you have more years of education. In the previous CEF, the outcome Y is different from every level of education, gender description, and race description. That combination is a subpopulation. So when I trace out this CEF, I'm going to fix the other X variables temporarily. But when I estimate a CEF, each one of these slopes is a venue for the values of the variables to change. And obviously, you can plug in any value of X that you want and produce an expected value of Y. So conceptually, this is where I want to start with regression. I want us to start with this idea that we are analyzing Y at many, many different subpopulation levels, and we're manipulating the characteristics of the subpopulation in order to produce different conditional estimates of Y of interest using this linear conditional expectation function.